Hello, integrated scientists, Mr. B. We're going to finish up section 3 of the life cycle of stars. Today we talked about what will determine the size of a star and again how long they will live if they are compared to a blue star, yellow star, or red star. So now we're going to talk about what actually happens to a star when it runs out of the fuel, because that was kind of the big thing from yesterday, is how long it takes it to run out of fuel, and now we're going to talk about is what actually happens when that fuel is gone. So the dwindling supply of fuel in a star's core ultimately leads to the star's death, and when the star dies, it doesn't just disappear, it can kind of be transformed into something else. We have what are called white dwarfs, neutron stars, or black holes are our three options there. So for the death of a star, so before we get to the three possibilities, they kind of all follow a similar pattern before they lead to one of those three possibilities. So when a star's core begins to run out of hydrogen, gravity gains the upper hand over pressure, and the core starts to sink. Again, we talked about that equilibrium between the thermal pressure from nuclear fusion and the inward pull of gravity. They balance each other out. Well, when they run out of hydrogen, that nuclear fusion stops and the core starts to shrink because gravity starts to push in, and again, like I said, it gains the upper hand. So the core temperature, as it gets pushed in, it rises enough to cause the hydrogen in a shell outside the core to begin fusion. Um, the energy flowing outward increases, causing the outer regions of the star to expand. The expanding atmosphere moves farther from the hot core and cools to red, and the star becomes a red giant. So those are kind of the steps it follows. Again, um, as it sinks in, again, more pressure is being put on the core. As more pressure is being put on the core, the temperature rises. Um, as that temperature rises, energy flows outward, causing things to expand. So it's almost kind of like it starts by shrinking. The shrinking core then generates more heat, and then that more heat then kind of makes the whole star expand together, and then the star becomes a red giant. Um, Again, the collapsing core then continues to grow hot enough for helium fusion to occur. So again, a majority of nuclear fusion, when it's going on, it's just hydrogen being fused to helium that's released massive amounts of energy, and it's the fuel for the sun. Well, then, as that temperature increases, as gravity starts to gain the upward hand, then helium will fuse to produce carbon, then carbon to produce oxygen, and so on and so on and so on, and it will work its way all the way up to iron. Actually, the elements will keep fusing until they reach their way all the way up to iron. Um, in helium fusion, the star stabilizes and its outer layers shrink and warm up. And again, the next kind of stage after this helium fusion depends on the star's mass. So this is where we can kind of deviate and go some different directions um, depending on the mass of the star. So here's going to be some of the options. Again, all stars start as a nebula, then they become a protostar, and then they follow the main sequence. Um, then after main sequence, they either become a red giant or a red supergiant. Then they can become a planetary nebula, then a white dwarf, or they can go through a supernova, neutron star, and black hole. So these are our three end games here. Um, After the death of a star, again, these are kind of the formation that we talk about early on. Again, that they all go through similarly, and then depending on which mass. Again, what mass you have. Again, if you're a low mass star, you're going to follow this path. If you're a higher mass star, you're going to follow this path right here. So low and medium mass stars are what we're going to look at first, kind of the top part of that picture. They can be as much as 8 times as massive as the sun. Um, Eventually, will turn into a white dwarf. So they can be 8 times bigger than the sun, but they can also be smaller than the sun. So after they go through their death stage, or their stage where they start to run out of fuel, they remain in a giant stage until their hydrogen and helium supplies dwindle and there's no other elements to fuse. So um, they go through that core kind of being shrunken in. Again, they're still fusing while that's going on, but once they run out of that energy, the energy from the stars it starts to decrease. Again, that thermal energy coming out decreases, and then with the less outward pressure, the star is going to collapse. Again, gravity is going to finally win that battle, and the star is going to collapse overall. The dying star is surrounded by a glowing cloud of gas called a planetary nebula. Again, remember we said as it heats up, energy starts to travel outward from that hot core and kind of spread out, so that could form our planetary nebula. Um, Again, as the dying star blows off much of its mass, only its hot core remains. So again, everything's kind of being shed from outside. Again, it's collapsed, and then again, it forms that cloud of all of the mass and the material that have come off from the star. This dense core is known as a white dwarf. A white dwarf is about the same size as Earth, but has about the same mass as the sun. So it's a much, 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 much more dense object. Again, if you took the sun and compressed it down to the size of Earth, that is what a white dwarf is. So again, it's not an overly large object, but it has so much mass that makes it up. Um, Again, and when a white dwarf, they no longer undergo fusion. They only glow faintly because they have leftover thermal energy from the fusion that they've been carrying out for billions and billions of years. And here's an example. Here's a planetary nebula. Again, this is called the Hourglass Nebula. As you can see from its distinctive shape there, kind of looks like an hourglass. Again, you can see the cloud and gas surrounding the collapsing red giant. Again, and what will be left over is a white dwarf there in the center. Then we have what was called the Crab Nebula. This is a remnant of a supernova explosion, which we'll talk about what a supernova is here in a moment, that was observed on Earth in AD 1054. This supernova was so bright that people could actually see it in the daytime. So again, this is going to be an explosion of a star that we'll see in a moment, but this is just kind of an example of kind of two different options of the death of the star. We have a planetary nebula, and again, this is a supernova, which, again, it comes up there in a couple slides there. So, again, lower mass stars, they will form what is called a white dwarf, which, again, going back to our picture here, a little flow chart here. Again, if you're a low star, you'll be a red giant at one time. Planetary nebula, then you become a white dwarf. Now we're going to lead now to our higher mass stars, which they start as red supergiants. Again, the life cycle of high mass stars is very different from that of the lower mass stars, which we can again see in our little flow chart there. As high mass stars evolve from hydrogen fusion to the fusion of other elements, they grow into brilliant supergiants. So they're very huge. Again, they create new elements, the heaviest being iron. So again, they continue to fuse elements. They fuse hydrogen to helium. They fuse helium to carbon. They fuse carbon to oxygen. It just keeps going and going and going. And then a high mass star, when the time comes when it runs out of fuel, the process comes relatively quickly because it consumes fuel very rapidly. Again, we talked about that early on. Again, the blue stars don't have as long of a life cycle because they burn so hot. They burn so much more quickly. So again, same with that high mass star. When they die quickly because it's going to consume this fuel rapidly in its core there. And as the fusion slows the high mass star, the pressure decreases. Again, gravity eventually overcomes the lower pressure, leading to a dramatic collapse of the star's outer layers. So the collapse, when they are that large, and those high mass stars will produce what's called a supernova, which is the explosion so violent that the dying star becomes more brilliant than an entire galaxy. So you got to think these giant blue stars have so much mass to them. They've been undergoing fusion with so much energy. Again, there's a ton of mass there. Again, think of our sun and just magnify it I think 300,000 times possibly. Again, that explosion creates what's called a supernova. Again, the release of energy makes it more brilliant than an entire galaxy. So supernovas, again, like I said, this Crab Nebula right here was a supernova, just huge amounts of energy being released. It was even visible during the daytime. Again, they produce enough energy to create elements heavier than iron. So again, iron is the last element that fusion will create, but then supernovas can create elements heavier than that. Again, these elements and the lighter ones, such as carbon and oxygen, are ejected into space by the explosion. As a supernova spews material into space, its core continues to collapse. So again, we see the supernova, it's one violent explosion there, but then the core continues to collapse after the supernova occurs. So that's not even the last stage for these stars. Again, the supernova is just the initial quick bang, where we've collapsed, but now what's going to happen? So then after the supernova, there's still a core left over. If the remaining core of a supernova has a mass less than about 3 times the sun's mass, it will become what's called a neutron star. So these are kind of the smaller big stars will become neutron stars. Which a neutron star is the dense remnant of a high mass star that has exploded as a supernova. So again, the most massive stars don't form neutron stars. These are kind of like one step up from the sun here. Again, in a neutron star, electrons and protons are crushed together by the star's enormous gravity to form neutrons, and then they're much smaller and denser even than white dwarfs. So neutron stars, again, small, dense thing. Again, protons and electrons smashed together to form neutrons. Again, a very dense area there. And as neutron stars spin more and more rapidly, they contract. So as they contract, they spin more and more rapidly. Again, some neutron stars spin hundreds of turns per second. So again, they even added an exclamation point there to say how fast that actually is. The neutron stars will emit steady beams of radiation in narrow cones. So again, as they spin, they're shooting off radiation. Again, the spinning neutron star then appears to give off strong pulses of radio waves called a pulsar. So again, and there's there's a little picture there again. Here's a neutron star spinning and spinning and spinning, giving off beams of radiation, and some of these beams of radiation even get sent to Earth. Again, that's how we can detect them. That's how we have evidence that this is actually going on, because we can feel them pulsing across our Earth there, or we have tools that can detect them pulsing across of our Earth. So our last option here for the death of a star, again, we kind of had, small stars become white dwarfs, get more massive stars become neutron stars, and then the biggest stars, again, if a star's core after supernova explosion is more than about 3 times the sun's mass, it's going to still have a very strong gravitational pull. Again, it's going to collapse beyond the neutron star stage to become a black hole. Again, black holes are objects that, again, have a lot of mystery behind them. Not really sure. Again, you have to ask someone a little bit more advanced than me to give you more explanation of what black holes are capable of. Again, a black hole is, just to give a definition according to your book, is an object whose surface gravity is so great that even electromagnetic waves traveling at the speed of light cannot escape from it. So black holes are known for kind of sucking things up. Again, have people ask me some question, well, what's on the other side? And I really just don't have a great answer for you on that one. But I think that's it for our transitions from the death of a star. Let me know if you have any questions.